Understand the relationship among visual elements such as lines, angles, and edges is important for their perception of the objects that populate the world. This skill helps them understand how different parts fit together to form a whole object. Size constancy is the perception that an object's physical size remains constant even though the size of its image on the retina changes. For example, when you see a car driving away from you, it appears smaller as it gets further away. However, you still understand that the car's actual size hasn't changed, even though its image on your retina has become smaller. Visual constancies, like size constancy, are important because they help infants understand that the world is stable. Without such constancies, every time a baby saw an object at a different distance, orientation, or light, it would appear to be a different object. Let's take a peek at the experiment of infants' size perception. Infants were first familiarized with either a small or a big cube shown at different distances. During the test phase, both big and small cubes were presented at varying distances, with the bigger cube placed further away and the smaller cube closer, making the images appear the same size on the retina. Interestingly, newborns show a preference for the larger cube, indicating they could distinguish between two cubes despite the equivalent retinal images. This suggests that some level of size constancy is present at birth. Our knowledge of objects extends beyond the various constancies. For example, when a person stands in front of the table, blocking the midsection of the table from our view, we naturally infer that two ends of the table are connected. In a sense, we perceive a full table. Do young infants also perceive objects as continuous and a whole when they are partially blocked by other objects? The occluded rod experiments by Kelman and Spelker provide a systematic explanation of how infants perceive motion cues. In these experiments, infants are first habituated to the movement of a occluded rod. After this familiarization, they are shown either a whole rod or a split rod moving in the same way. If the infants have formed an expectation that the rod is a single continuous object, they will find the split rod more surprising and will look at it longer. This reaction indicates that they perceive the joint movement as belonging to a whole object. Newborns do not show a difference in looking between whole and split rods, indicating that they do not have an expectation of object wholeness yet. By the time infants are 4 months old, they look longer at a split rod when they have been habituated to a simple side-to-side movement. This suggests that they already interpret synchronous movement as a sign of unity. However, if they are habituated to more complex rotational movement, they show no preference. By 6 months and older, infants look longer at the split rod, even with more complex rotational movement, demonstrating a progression in their development with age. When objects rotate, their shape appears to change, which is referred to as a shape constant. Have you ever noticed, for example, when you approach the dinner table that the shapes of the plates do not change? When you look at them from some distance away from the table, the shapes of the round plates are elliptical on your retina. The only time that the image of a round plate is approximately round on your retina is when you look at it straight on. Additionally, changing in lighting conditions affect how brightness and color are perceived, known as brightness-color constancy. Color constancy is the experience that the color of an object remains the same, even though the wavelengths it reflects back to the eye change due to the changes in the color of the illuminating light. For instance, a red apple will still appear red to our eye whether it's viewed under the sunlight or indoor lighting. Similarly, brightness constancy means that an object, like a white piece of paper, will appear white whether it's in bright sunlight or in the shade. Infants typically achieve all these perceptual abilities after approximately 4 months. Infants must also be sensitive to what happens to objects out of view. Balajian demonstrated that even at 4.5 months, infants have some sense of object permanence. The infants were habituated to a solid screen that rotated back and forth through a 180-degree arc in the manner of a drawbridge. Following habituation, a box was placed behind the screen, and the infants were shown 2 test events. In one possible event, the screen rotated until it reached the occluded box. In the other impossible event, the screen rotated through a full 180-degree arc as though the box were no longer behind it. The infants looked longer at the impossible event when the box seemingly disappears, indicating they have a sense of object permanence. It's argued that object permanence is not initially specified but develops over time. Object permanence grows from prior understanding of object identity, the spatial-temporal criteria that infants use to predict a future encounter with an object and re-identify as the same one after a break in perceptual contact. These identity criteria allow infants to understand that a disappearing and reappearing object is the same one. Maintaining this identity over disappearance transformation is essential for acquiring object permanence from real-world experience. It's further argued that different types of occlusions have varying identity demands, which is why some develop later than others. The findings suggest that young infants' understanding of permanence is not an all or none phenomenon, but a work in progress during infancy. As babies acquire the ability to move around, they also develop the capacity to get into trouble. One potential danger is falling over edges if they cannot perceive that a surface that supports them drops off. Eleanor Gibson and Richard Walk first tested infants' perception of depth using a unique device called a visual cliff. The visual cliff consists of a sheet of plexiglass on which the infant can crawl. A patterned cloth lies just beneath the clear surface on the side, while the other side the same cloth pattern lies several feet below in the clear surface. Infants able to crawl were placed on a small platform just at the edge of the boundary between safe and deep zones. Although their mothers called to them across the deep side, most infants were unwilling to cross, apparently because they perceived the depth and danger. Subsequent research has confirmed the pattern identified by Gibson and Walk. Most babies old enough to be tested avoid the deep side of the cliff, and by 9 or 10 months, This avoidance response is quite strong. The head rate of infants as young as 1.5 months of age slow when they are lowered to the deep side. These findings tell us that the babies notice the difference and are interested in it. There is no evidence, however, that they can fear the depth. By 9 months, the response is quite different. Now the head rate increases over the drop-off, suggesting that babies are afraid, and now most infants are also unwilling to cross over the deep side. The shift from interest to fear in response to drop-off occurs after about 7 months of age, when many babies start to crawl. There is a correlation between crawling experience and fear of death. Babies who have been crawling the longest are most likely to show the fear response on the visual cliff. But what cues do infants use to perceive death? There are two types, kinetic cues and static ones. Kinetic cues, to which infants are sensitive from as young as 1 month, include visual expansion, where objects appear larger as they get closer, such as when a ball is rolled towards them. Motion parallax is another kinetic cue, where objects moving nearly cross our visual field faster than those moving farther out, like when looking out of a car window and noticing that nearly trees move faster than distant mountains. Static depth cues, to which sensitivity appears from 4 months, include retinal binocular disparity, where there is a slight difference between what the left and right eyes see. The closer the object, the bigger the difference. Texture gradient is another static cue that appears at approximately 5 months of age, where nearly objects show more detail, such as the individual blades of grass in a lawn. Lastly, linear perspective is a static cue where parallel lines appear to converge in the distance, like railroad tracks meeting at the horizon. Keeping track of locations in space involves two types of spatial encoding, egocentric and allocentric. Egocentric encoding means the understanding of space and object is tied to one author's action and body. For example, babies who find an object to their right expect to find that object on the right again, even if they rotate their body. Allocentric coding means the understanding of space and object is tied to other objects and landmarks in the environment. Early in development, babies understand the word egocentrically using egocentric coding. Gradually, they shift to allocentric coding and learn to use stable landmarks in the environment to find objects, as these provide reliable cues that do not change as babies move around. This shift reflects that the young infant only gradually learns the distinction between the self and external world of objects. A study by Linda Akredlova examines this developmental shift in spatial coding for infants at 6, 11, and 16 months of age. Infants learn to turn and look at the window to make an interesting visual display appear. For half the infants, a colored star around the window served as a landmark. After the infants learned the left turn response, the chair was rotated 100 degrees so that the correct response was now at the right turn. 6 months old turned to the left side using the bodies rather than a landmark as a frame of reference. 11 months old also tend to turn left when no landmark was present, but were able to use the landmark to respond correctly when it was present. 16-month-old responded correctly whether the landmark was present or not, showing a clear progression with age in the ability to use external references to judge spatial location. Self-produced movement facilitates understanding of locations, as infants who move on their own perform better on such tasks than those who are carried. Additionally, infants who have begun to crawl do better on these measures than those who are not yet crawling. Clark Preston criticized the work of Linda Accredolo in the study, found that if the mother was not turning with the baby, that infant from 9 months of age could use the mother as a lamp.